Here we're going to consider something that confuses many students, which is to say, what is the relationship between the normal force and weight, and are they an action-reaction pair? Before we do that, let's first remind ourselves what Newton's third law says and what action-reaction pairs are. So here I have the actual Latin that Newton wrote in his book, because the language that was used for academic works at the time was Latin. Translated into English, what he wrote was, to every action, by action he meant force, there was always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. The second phrase is probably a little bit better because he does here specifically call a force a mutual action or an interaction between two objects. We can translate this into mathematics by writing this equation right here, which really says the force that object A exerts on object B is equal and opposite to the force that object B exerts back on object A. That just takes the words that Newton wrote and puts them in the form of an equation. Some things to note about this equation. First, which is what everyone always remembers, is that the forces are equal and opposite. That's what the equal sign and the minus sign mean. However, there's two other things to remember. First is that the forces are always on two different objects. One is acting on object B, the other is acting on object A. They are not forces acting on a single object. Another thing is that there are exactly two objects involved. He's talking about the mutual actions of two bodies upon each other. There's no third body involved. So the three key points to bear in mind when we're talking about Newton's third law is the thing everyone remembers, the equal and opposite part. The two other things you have to remember is that the forces are in different objects and there are only two objects involved. So now let's go back to you standing on the floor. What forces are acting on you? Well, there's gravity, which is pulling down on you, and the normal force from the floor, which is pushing up on you. We can draw those two in as vectors, so we have the force of gravity going down and the force of the floor going up. Now, these forces, Newton says, are always interactions between objects. Gravity is actually an interaction between you and the Earth, and by the Earth, we really mean the interior of the Earth. So we'll write that down. The force of gravity is actually the Earth pulling down on you. The normal force is an interaction between you and the floor under your feet, so we can say the normal force, or the force of the floor, is equal to the floor pushing up on you. Now, we can identify the reactions to those forces. To get the reaction, you take the two objects and swap their places in the line, and then you reverse the direction of the force. So we take those two objects and we swap them, and we take that direction and we flip it around. So for the force of the floor, the reaction to that is you pushing down on the floor. So we take these two objects, we flip them around, take that direction and reverse it, and this is what we get. Notice gravity is not involved. Down here, we do the exact same thing, and the reaction to your weight is you are actually pulling up on the Earth. So, like it or not, you're basically holding up the Earth. Now, let's look at the causes of these forces. What actually causes the normal force? Why is the floor pushing up on you? Here we might consider the following. The floor is made up of atoms, and as you've discovered, atoms are mostly empty space. You are also made up of atoms, and your atoms are just as much empty space as the atoms in the floor. How does empty space hold you up? Well, atoms consist of basically a tiny nucleus, which is where most of the mass is, and that's at the core or the center of the atom, but surrounded by electrons, which are light, but they have just as much charge as the nucleus has. It's just that this charge happens to be negative. So what we really have is electrons on the outer part of the atoms repelling each other. So what we have, electrons in the outer surface of the floor, which are negatively charged, and we have electrons on the outer surface of your feet, and those two will repel each other. Or it is really an electrical force that is holding you up, and it's the reason you don't fall through the floor. While the atoms are mainly devoid of mass, they are filled with charge, and particularly the outer layers are filled with negative electrical charge. and those electrical charges repel each other. Here we have Bryan Adams in the video from Nova, The Elegant Universe, who actually describes this.
We tend to think that gravity is a powerful force. After all, it's the force that right now is anchoring me to this ledge. But compared to electromagnetism, it's actually terribly feeble. In fact, there's a simple little test to show this. Imagine that I was to leap from this rather tall building. Actually, let's not just imagine it. Let's do it. You'll see what I mean. Now, of course, I really should have been flattened, but the important question is, what kept me from crashing through the sidewalk and hurtling right down to the center of the earth? Well, strange as it sounds, the answer is electromagnetism. Everything we can see, from you and me to the sidewalk, is made of tiny bits of matter called atoms. And the outer shell of every atom contains a negative electrical charge. So when my atoms collide with the atoms in the cement, these electrical charges repel each other with such strength that just a little piece of sidewalk can resist the entire Earth's gravity and stop me from falling. In fact, the electromagnetic force is billions and billions of times stronger than gravity.
Okay, that's obviously a demonstration you don't try at home. Now we're going to consider gravity. Weight is the force between you and the Earth, and it's the entire Earth pulling on you. Even though we often refer to the ground under your feet as you standing on the Earth, that's not what we mean here. Here we mean every single atom of the entire Earth pulling on every single atom of you. That's what constitutes this force right here. It's not just the ground under your feet, it's the entire Earth. So the question is, where do we find most of the mass of the Earth? And the answer is we don't find it on the surface. We find it deep in the interior. Much of the mass is in the core and the mantle, which is fairly far away. It's like kilometers away. Interaction between you and the Earth is really an interaction between you and the entire Earth, and really means the interior of the Earth. That's an important point to remember. So now let's go back to our original question of whether or not weight and normal force are action-reaction pairs. We discovered that weight is really an interaction between you and the interior of the Earth. The normal force is an interaction between you and the atoms directly under your feet. Action-reaction pairs are always equal and opposite. Generally speaking, for weight and normal force, that will be true. But that's only a part of what we mean by an action-reaction pair. An action-reaction pair have to act on different objects. Here, that's not true because both weight and normal force are acting on you, not on two different objects. Finally, there can be only two objects involved, and we're talking about weight and normal force. We actually have three objects. We have you, both the forces are acting on you, but they're from two different objects. One is the dirt under your feet, which really means the atoms under your feet. And the third object is the interior of the Earth, which means atoms very far away from you, including atoms in the core of the Earth. So there are three objects involved, which means they cannot constitute an action-reaction pair. In addition, there are two different types of forces. One force is a gravitational force, which is caused by the mass of the atom, and the other is an electrical force due to the fact that electrons have negative charges. So they cannot be an action-reaction pair. Typically, weight is equal to the normal force. That is often true, but that's not a fundamental law of nature. You certainly can walk into a room and discover that the floor is made of rotten timbers, and you can fall through the floor. While you're falling through the floor, the force between you and the floor will be equal and opposite between you and the floor and you. In addition, while you're falling, gravity of the earth will be pulling down on you just as hard as you're pulling up on the earth. Those will be action-reaction pairs and will be equal. However, the force that the floor exerts on you will not be equal to your weight. It'll be less than your weight and you will fall. Typically that doesn't happen, but that's due to the fact that we have building codes or government regulations that require that floors in buildings should be strong enough to support whatever load is likely to be put on them. And that's not a law of nature. That is a building code. So while this is typically the case, that weight usually is equal to the normal force, that is not a fundamental law of nature. It is not due to Newton's third law.